The beam that's shown here is supported at three locations, A, C, and D. A roller supported A and C, a pin joint at D. There's a constant line load of 5 kilonewtons per meter over the entire length of the beam. We want to know what the shear force and bending moment diagrams are for this beam. If we would look at FBD of the entire beam, which stretches from A to D, the forces that we would have on here would be the resultant load, which would be 5 times 4 or 20 kilonewtons. We would have a vertical support at A, a vertical support at C, and a vertical support at D. Indeterminate. At least based on this FBD. But however, we can still solve it. We can still end up with the shear force and bending moment diagrams. What we will do is we will break it up into two parts. We'll look at A and B, and the forces we have acting over AB is going to be the line load. The equivalent line load there is going to be 10 kilonewtons. There will be a reaction force on this member, this piece of it, of AY on the left side, and CY, I'm sorry, that's not CY, that's BY on the right side. From this, when I do a moment about A, I get BY times 2 minus 10 times 1. So from this we see that the reaction force at B is 10. Summing forces in Y, we get AY plus BY minus I'm sorry, I wrote down the wrong thing. This here should be 5. And this one would be minus 10. For equilibrium, that says then the AY is also equal to 5 kilonewtons. So this is for member or section AB. For section BC, I draw a free body diagram. The forces that I have acting on that, there's going to be a 10 kilonewton force in the middle due to the line load. Recall I put BY upward there on member AB. On BD it's the opposite way, down. I've got a reaction force at CY, reaction force there of DY, summing moments about point D gives me minus CY with a moment arm of 1. The applied force resultant there of 10, it's got a moment arm of 1, and I have BY, which has a moment arm of 2. So from this section we see that CY will be equal to 20 kilonewtons, and summing forces in Y, I get minus BY plus CY plus DY. For equilibrium, it says that DY, interestingly enough, is the other way, and that's a minus 5 kilonewtons. So note that by breaking this beam up into its two sections, we were able to make it determinate. So now we're going to be tackling the shear force. We know that the shear force is the integral of the load, and so what I can do is I can calculate what the shear force is all the way over on 3 by setting it equal to what it is on the left hand side plus the area under that curve, so that's minus 5, minus sign because it's down, over the length there of 3. So that will end up being a minus 10. VO we found is the same thing, or that is the same thing as AY, and we found that to be a positive 5. Okay. So it starts out with V being a 5. We know it goes down to a minus 10. Since the line load is a constant, the area under the constant curve ends up being a linearly decreasing function of x. So let me call this 3 minus, because it's immediately, oops, I totally botched that one. So let me try this again. Let me erase some of my work. What I mean by this is I should have drawn it all the way over here to 3, not to 2. So let me do my best to draw this straight line like that. So again, this is at minus 10. And so this is going to be 3 a minus. It's immediately to the left of C. I make that distinction between immediately to the right, which is called 3 plus, because there's that point load there of CY. So that's a jump up. So that's 3 minus location there for V plus CY. So that's equal to minus 10 plus CY that we found was equal to 20. So at that roller support, it jumps up to a plus 10. V at 4, which is over on the right hand side. That's V at 3 plus minus 5 times the distance over which that acts is a 1. So this becomes a 10 minus a 5. So that ends up being a plus 5. And please note that that checks out, because we know that needs to be, if I write dy as this, recall that on the right face, shear force is positively down. So that's going to be a minus d, and a minus d is equal to a plus 5. So that checks out. So it's always good to develop whatever checks we have got in order to see if our answers are correct. But let me finish up on this by saying I complete my shear force diagram like that. So this is how V looks. There's going to be a point of interest for us here wherever the shear force crosses the x-axis. And the reason for this is that at this point of x, which I will call x naught, that's where the bending moment is going to be a maximum. So before we get to there, let's figure out where x naught is. So V of x naught, by looking at the figure there, is equal to a 0. So that's equal to V on the left hand side plus minus 5 times x naught. So that's equal to 5 minus 5x naught. So therefore we see that x naught is equal to 1. So it happens there at 1. This is 2 and 3 and 4. So what I will say is that the bending moment at that value of x naught is equal to m on the left side plus the area under the shear force curve is 1/2 5 times the base there, which is x naught. M sub 0 is a 0 because as far as a moment goes, end A is free. So this becomes, where x naught is equal to 1, that becomes 2.5. So what that means is that we have a maximum for m. And that maximum value is 2.5. Again, very important to note that what we used here, if I sort of draw this off to the side, is that we know that shear force is equal to dm dx. Any place that the shear force is a 0, that says that the slope is a 0. And so that's why I drew that as I did. We can now write m at 3 as being m at x naught. We just found that. That's 2.5. The area under the shear force curve, it's 1/2 the base, which is 3 minus x naught, times the height there, which is minus 10. That, therefore, is equal to 2.5. This is a 1. So it's minus 10. So that ends up being minus 7.5. We know that the bending moment was a 2.5 over there at 1, and that means then here at 3, when I make this minus 7.5, the bending moment looks like this. And when you draw in the m, please make sure that the bending moment curve is a 0 there at 2. Why is that? Well, if you look back up here at our picture of the beam, there's a pin joint there at B. So since a pin joint cannot transmit a bending moment from one side to the other, that has to be a moment-free point. If you do the math, it works out, but we know that, so let's take full advantage of that. Now if I want to figure out what it is at 4, the bending moment at 4 is the bending moment at 3, and in this case what I have is a trapezoid. So I'm going to break the trapezoid up into two parts. I've got a triangle, area is 1/2 the base times the height, and then I add on to that a rectangle. So the area in this case is going to be equal to the triangle on the top is 1/2 5 times 1. The rectangle part is going to be equal to 5 times 1. So this is going to be m at 3 is minus 7.5 plus 5. The 5 is correct, but I have it in the wrong spot there. 2.5 plus 5. So that is equal to a 0, and that checks too, because the right end is a pin joint to ground, and again, pin joint cannot transmit moment from one side to the next. So in this case, our bending moment ends up here, and since the math checks, that's somewhat reassuring to us that we have done things right as we move there from left to right. So in summary on this problem, when we first looked at the beam, it appears to be indeterminate. But if we take advantage of that known information that there is a pin joint there at B, we can break it up at that point. We can solve for the reactions on each part. An important thing here is that when we found by here, the equal and opposite one has to be there. And when we did equilibrium in that piece, we found cy and dy. After that point, it's a regular kind of shear force bending moment diagram. We start from the left and we move to the right. Along the way at each section, the line load is a constant, and then we have these concentrated loads one there at A, one at C, and then one at D. So we carry through with our integration that we do by the graphical means.